All right, let's start off with some discussion about direct and inverse variation. Have you ever done direct or inverse variation before? So the answer is yes. You've done both, okay? But probably, or maybe it wasn't discussed as direct variation or inverse variation, okay? So we're going to do a couple of these problems together, and then I'm going to ask you that question again, all right? Because I want you to notice some things about what we're doing, all right? So let's start here. A square with side length x units has a perimeter of y units. How are we going to set up an equation about that square? So how do you find perimeter? Add up all the sides, right? What's special about the sides of a square?
They're all the same.
They're all the same, so the perimeter y is going to equal what? 4x. Very good. Okay? So if you know that x is 3, what is y? 12, because 3 times 4 is 12, right? If you know x is 7.5, what is y? Close. It's just 30. Okay? Think about this. Guys, I want you to realize that multiplying something by 4 is multiplying it by 2 and then by another 2. Isn't it? Because 3 times 2 is 6 times 2 is 12, right? So isn't that the same as multiplying 3 times 4? So what is 7.5 doubled? 15. Can you double 15 pretty easily? Yeah. Okay? Now, I know it took a long time to get that answer, but I want you to try to get a little bit more comfortable with doing things like that, doing math problems like that, so that we don't always have to rush to our calculator. Do we sometimes want to use our calculator to check our answers? Oh, yes. Okay? But I want to try to get us a little bit more comfortable with numbers like this. And I'm being honest when I say us. Okay? I'm working on this as well. Right? So what about this one? What is 4 times 9.5? 38. How did you do that? Very good. You know what they did earlier? They did 10 times 4 is 40.
Miss Kingston?
Yes, ma'am?
Can you send Alex Ferris to the office real quick?
Does she need to come right now?
No, it's fine.
Okay, thank you. She'll be there in a little while.
Thank you.
They did 10 times 4, which is 40, and then they knew they had 4 little halves that didn't count. So they took away 2 and got 38. Did they still get the same answer as you got? Yeah? So is there a right way or a wrong way to do that? No, just a different way that people think, right? All right, what about number 2? A rectangle with a length of x units and a width of y units has an area of 60 units. Close. How about this? Yeah, x times y, right? Area is length times width. You remember that? Okay. Is this how we're used to looking at equations, though? It really isn't, right? How are we used to looking at them? Y equals, right? Well, what would this equation be if it was y equals? 60 over x, right? If we're trying to solve for y, which of these equations is a little bit more useful? The second one, right? The one that's solved for y already. We're trying to figure out what y is. So would it be better for me to say 4 times x equals 60 and then divide both sides by 4? Or would it be better for me to say 60 divided by 4 is what? Probably a little quicker when it's already solved for y, isn't it? Okay, so what is 60 divided by 4? 15. What's 60 divided by 8? Do you know? 7.5. And then what is 5? Okay. How did you figure out that this was 5? Oh, okay. So there's several different ways to think about that one too, isn't there? Okay. So 5. Let's do one more and then we'll go back and talk about the question I asked at the beginning. A man 5 foot tall casts a 3 foot shadow. At the same time of day, a tree Y feet high casts an 8 feet shadow. How are we going to set up that equation? It's like a ratio or proportion, right? Okay, so for the record, is there only one way to do ratios or proportions? Guys, I can think of 4 right now. I can think of 4 different ways to set this up. Okay, so let's just come up with one of those ways and we'll go from there. How about that? Okay, so what do you want to do? Yeah, but we have to set up the equation first. That's one of the ways. We can do y over 5 equals x over 3. Because we have tall part of the tree over tall part of the tree. So then we have, of the person. And then short part of the tree over short part of the person. Does that make sense? So how would we figure out what this is? I mean, this is a pretty useful, kind of useful equation right now. But wouldn't it be better if it was just y equals? How would I get rid of the 5 then? Yeah, it's in the denominator, right? So I'm going to multiply both sides by 5. When I do that, I get y equals 5/3 x or 5x over 3. Either one of those is fine. So what if x was 4.5? What is 4.5 times 5 over 3? 7.5. What if x was 9? 15. What if x was 10.5? 17.5. Yep, that's right. Okay. What about this number 4? A person 60 inches tall looks through a mirror 30 inches from the wall. If she's x inches away, how far y up the wall can she see? Is this the same kind of question as number 3? Yeah, it is, right? So what proportion do you want to set up? Do we know this height right here, by the way? That's 60, so let's go ahead and label that so we know that for sure. That'll help visual people. Y over 60. So we did shorter over shorter. 30 over x. Okay. Perfect. Multiply both sides by 60. So that simplifies to 0, or excuse me, that simplifies to 1 right there, and I get y equals 1800 over x, right? So what if x is 20? What's y? 90. What if x is 40? What is y? Close. 45. Guys, maybe I led you the wrong way of thinking earlier. Are you allowed to use your calculators when we're doing this computations? Absolutely. Okay? Think about it with your brain first, and if you can't figure it out pretty quickly, yeah, use your calculator. Okay? If you sat here long enough, you could figure it out. We don't have long enough. Okay? We have this class period to get this done and talk about it. Understand it, explain it, ask questions and stuff like that. So that's why in high school, I don't mind using a calculator when we're doing our arithmetic. Because we've already talked about arithmetic in other places. We've already talked about even faster way to do some of the arithmetic that we know. But when it starts to interfere with the math that we're trying to do right now, we're going to use our calculators, and that's okay. All right? So what about if x is 60? 30. That one was pretty easy, right? Excuse me. All right, so let me ask the question I asked at the beginning again. Have you ever done direct and inverse variations? Have you ever seen an equation that looked like y equals 4x? Yeah, in fact, most of the time it was in Algebra 1 or even in 7th grade, 7th or 8th grade, when you talked about I think that you even talked about it as direct variation. And when you didn't, you were suddenly presented with a form that looked like y equals mx plus b. Oh, yeah, slope-intercept form, right? Now, all the b did was transform it using transformations either shifted up or down, right? Based on our discussion about transformations lately. But without the b, y equals mx, isn't that in the same form as direct variation? Okay, so you've done that before. What about inverse variation? Have you ever done this before? You might have on accident. It doesn't show up in the TEKS until Algebra 2. Okay, so that's kind of why we're doing it right now. I'm trying to compare stuff you already know with stuff that's new. Okay, so let's look at the last example on that page. Number 5 and 6. For X people to travel, the cost Y in dollars for renting a bus at $7.50 per person. So the cost of renting a bus is, very good, 750x. Okay. So what about if x is 10? What's y? Very good. What about if x is 25? What is y? 187.5. Did you do that in your head? Perfect. What about if x is 30? What's y? 225. Everybody okay with this? This is pretty simple substitution right now, right? Okay. What about number 6? The bus will cost $180 to rent. If X people ride, how much will it cost per person? Y. So X people to ride times the cost should equal 180, right? But then again, the same question as these other two above it, is that normally how we see an equation that we work with? Normally it's y equals, right? So this, in this case, it would be y equals what? Very good. Okay? Now, for just a second, I want you to stay on this page. Okay? I'm going to turn the page and go on, but I want you to stay on this page. Because I want you to be able to be looking at the problems that we just did, because the table on the second page asks, what do they have in common? And if you're constantly trying to turn back and forth, you're going to get confused. Or you might get confused. And I would rather stop that from the beginning if possible. Okay? So here's what I want. I want to start with this column right here. We're going to look at problems 1, 3, and 5 first. Okay? First of all, what do their tables have in common? Look at what kind of answer it wants here. If x blanks, then y blanks. What do you notice about the table in problems 1, 3, and 5? What is x doing in every single table in problem 1, 3, and 5? Say it again. It does equal to a number. I agree with that. But what else is it doing? Just the x values. Do you notice that x is increasing? On every table in 1, 3, and 5, is x increasing? Then tell me what y is doing. On every table in 1, 3, and 5? So if x increases, then y increases. True or false? Okay. What about their relationships? Look at the equations. Guys, I promise I'll give you a chance to come back and copy this in a minute, okay? Keep looking at 1, 3, and 5. Look at their relationships. In the relationships that x and y have is that they have a constant something. What is that a constant? What's it called? All of them look like y equals kx, right? Well, I guess I could just write that right here because that's the equation. That's what's coming next. But what if it was just solved for the constant? What would it look like? Doesn't it look like that? How are x and y related right here? What do they have? How is it set up? Looks like a fraction, doesn't it? What's another word that we know in upper level math classes that is called a fraction? Yeah, that's exactly right. I'm also going to put one more word because we've called it that before. When we talked about y equals kx, we talked about that either being the slope or the rate, didn't we? The rate of change. Okay, so we're going to call it a constant ratio or a constant rate. You okay with that? Okay, write those down real quick, and we'll go on in just a minute. So the tables, if x increases, then y increases. The relationship is that x and y have a constant ratio or rate. And the equations, I'd like for you to actually write both equations down. Y equals kx and y over x equals k. Are they really the same equation? They are, right? Just in a different form. You okay with that? Okay, turn back to the problems again, please. What do problems 2, 4, and 6 have in common with relation to their tables? What's x doing? Increasing. Whoops. If x increases, then y decreases. Well, that's interesting. X and y have a constant what? Well, let's look at the equations. Okay, what do their equations look like? Here's one of them, right? xy equals k, or y equals k over x, right? Okay, so if we're looking at this one, what are x and y doing to each other? Multiplying, so they have a constant. That's an English word. Product. Okay? They're multiplying, that's a constant product. You okay with that? Participle was a close guess, though. Okay, turn it over and copy these down, and then we'll stay on this after you're done copying. Okay? So what do problems 2, 4, and 6 have in common? Well, for their tables, as x increases, then y decreases. X and y have a constant product for problems 2, 4, and 6. And their equations look like either xy equals k or y equals k divided by x. Once again, are these the same equations? Yes, but in a different form, right? Okay, so now we have to figure out what they're called. What kind of equation is this called? Predicate adjective. Excellent. This is called direct variation. Okay, let's see if you can use your context clues. See, I'm going English on you. If this is direct variation, what's this? Inverse. Does it make sense that the inverse would be when they are multiplied as opposed to when they are divided? Yeah? Okay. So let's look at a sample question. Once I show you the sample question, you're going to know how to be able to do the homework that's on the next page. Okay? So what the sample question is going to say is it'll read, if y varies directly as x, and y equals 12 and x equals 8, then what is y when x equals 24? So it's going to give you two numbers that are already directly related. Okay? Then it's going to ask for what is one when the other is this. So the first thing you have to do, if you know an x and a y, what are you left to find? The k, right? Which one of these equations, even though we know they're the same, they're just set up in a different form, which one would be easiest to figure out k? Probably the one that's solved for k, right? So if we start with k, k equals y over x, and we know y and x, can't we just substitute that in? So k equals 12 over 8, which is what? You can do it. They're both divisible by 4, aren't they? Three over 2? How about 1.5? You guys are usually more comfortable with decimals than you are with fractions. Not that I've tried to change that, but it's okay. It's okay. Well, is this our goal? Is our goal to solve for k? Does it ask us what k is? No, it asks us for y. So now we have to start over. First, we solve for k. First, solve for k. Okay, we solve for k. Now it's asking us to solve for y. Which one of these two equations would be better to solve for y? The one that's y equals, right? So this time, though, I'm going to write y equals 1.5x. Because I already know what k is, right? Based on the information that they already gave us. Is k 1.5 for every problem that we do? No, it's not. That's what we have to figure out first is k. Now that we know k, we have to solve for... In this particular problem, we have to solve for y, but we have to solve for what they ask us for. Solve for what they want. Sometimes they'll want x, sometimes they'll want y. In this problem, they want y. Okay? Well, if they want y, they also have to tell us that x is something, so we can solve for it. So here I say y equals 1.5 times 24. What is 1.5 times 24? 36. And that is the answer. Okay? Questions? So what's the other one going to read? If y varies inversely, it's going to read if y varies inversely as x and y equals 12 and x equals 8, then what is y when x equals 24? Well, guys, that's super close to this other question. Shouldn't we just get the same answer? Because of this word, we absolutely will not. Okay? So, what do we do first? Solve for k. Which one of these equations do you think I ought to use if I'm trying to solve for k? Equals k, right? So k equals xy. Am I given an xy to solve for k? Right here. Y is 12 and x is 8. What is 8 times 12? 96. Now that I know k, what do I do next? Solve for what they want. And they want y, so would it make sense to use this other equation? This other form of the same equation. So 96 over what? So 96 over 24, right? Because that's what they tell us. What is 96 over 24? 4. Done. Now, before I let you go to work on these right here, because 5 through 10 you're not going to have any problems with. I'm still a little worried about 1 through 4. So do you mind if we talk about some of those? Let's look at number 1. It asks us to identify whether each table shows direct variation, inverse variation, or neither. How in the world do we look at a table and know if it's direct, inverse, or neither? Okay, so we look at increase and decrease, right? Okay, so on number 1, x is increasing and y is... So it's automatically... Really? If it's inverse, what else does it have to have? A constant product. X and y have to have a constant product. What's 4 times 110? 440. What's 5 times 88? 440. What is 8 times 55? So is this truly inverse variation? Yes, we can write inverse. Okay? What about problem number 2? Increasing, decreasing. So our first thought is inverse, but I have to check to see if it has a constant product. What's 4 times 11? 44. What's 5 times 10? 44? Oh, so what does that mean? Neither. Okay? looking at the table, whether it increases or decreases, is a very good way to start. Very good way to figure out the indication whether it's going to be direct or inverse. But if you decide it's direct, you have to make sure it has a constant ratio or a constant rate. And if you think it's inverse, I think I said inverse, I meant direct, I'm sorry. If you think it's direct, you have to see if it's constant ratio or rate. If it's inverse, you have to see if it's got a constant product. Does that make sense? Okay, so 1 through 10 is what I want you to do. Can you finish it for the bell? I dare you.